Welcome to Clean Energy Innovation at the Georgetown School of Foreign Service in the Science, Technology, and International Affairs program. My name is Varun Sivaram, and when I'm not teaching here at Georgetown, I'm the Douglas Dillon Fellow at the Council on Foreign Relations. CFR is a nonprofit founded in 1921 that's a think tank, it's a publisher of Foreign Affairs magazine, and it's a membership society dedicated to providing analysis and insight into U.S. foreign policy. Today's Lecture 1, Why the World Needs Clean Energy Innovation, and I'm excited to get started. To give you an overview of the course, we're going to be looking at one of the most important problems of the 21st century, and that's climate change and how the world can confront it. So should you be taking this class? Well, if you're a science major, or if you're a policy major, or if you're an economist, or if you're just an interested student or citizen who wants to help solve this problem, I think you're in the right place. And we're going to endeavor to build up an integrated view of the different components, be they economics, policy, or science, that all contribute to innovation. Clean energy innovation is going to be essential to mitigating climate change. We're going to need to adopt breakthrough new technologies, whether they're solar panels or batteries or clean fuels, at massive scales. And we're going to have to do so faster than we've ever done before. To get there, we're going to need three components of innovation. First, we're going to need technology and process innovation. This is where the scientists and the engineers and the entrepreneurs excel. But in addition, we're going to need business model innovation. How do we take both existing and new clean energy technologies to the market to commercialize them? And finally, we're going to need public policy that accelerates innovation. And that's where the government comes in. In this class, we're going to focus on the power sector, the electricity sector. Now, there are many facets to clean energy. Transportation, for example, or industry, and we're not going to deal specifically with those, although we will touch on them. Most of this course will be focused on the electric power sector. And the reason for that is, if you're able to clean up your electric power sector, you can then clean up downstream sectors, like a transportation sector that uses electric vehicles or electric mass transit. The key is going to be decarbonizing or cleaning up that upstream power sector. So within the power sector, in this class, we're going to talk about 7 major buckets of technologies. We're going to talk about solar energy and wind energy, geothermal, hydroelectric, nuclear, energy storage, and finally, we're going to talk about the electricity grid that ties all of these resources together and allows us to generate, transmit, and deliver clean power. This course is a 15-week course, and so I urge you to follow it all the way through because we're going to be going through 4 units that together compose a holistic picture of what clean energy innovation is and how the world can do a better job of encouraging it. The first unit is just going to set the stage, a context and overview. Today, we'll do a teaser lecture. Then in week 2, we're going to launch into a more theoretical understanding of what innovation is, not just in clean energy, but as understood in other fields. We've seen many revolutions, whether they're in the biomedical space, in the electronics and computing space, in the information technology space. How do we apply those insights to clean energy, and what's different about clean energy? Week 3 and week 4 are going to introduce you first to energy fundamentals. What is a joule? What's a kilowatt? And then we're going to get into the power sector in particular. How is power generated? How is it transmitted? Why is it that the United States electricity grid is widely considered the most significant engineering accomplishment of the 20th century? And why won't it suffice for the 21st century? The second unit is going to dive into some technical concepts. I don't want to scare you off here. We're not going to be using complex differential equations. We're not going to require that you know a lot of physics. We're going to endeavor to build technical fluency from the ground up. And so we're going to give you the basics on wind and solar power. These are known as variable renewable energy sources, or energy sources that are kind of unpredictable. You don't know when the wind is blowing or the sun is shining. Week 6 is hydroelectric and geothermal power. These are renewable energy resources that are a lot more predictable. Then nuclear power, week 7, is a form of energy that is clean and zero carbon, even though it's not normally lumped in with renewable energy. I think it's important that we discuss it in a course on clean energy. Similarly, carbon capture and storage. This is a way of taking carbon dioxide emissions that cause climate change out of a fossil fuel power plant and putting it into the ground. If we can do that, then we can continue to use a lot of the energy infrastructure that we already have. Finally, week 8 is going to be energy storage. This is, by many accounts, the most exciting field in energy innovation. Who's going to create the next battery that's going to power not only Tesla's electric car, it's going to power the electricity grid, and it's going to make solar and wind that are unpredictable sources much more predictable if it can smooth out their power output. Moving on from technology and process innovation. And when I say process innovation, I mean not just brand new solar panels, but also brand new ways of making solar panels or batteries. Moving on from that unit, we'll move into the third unit, which is business model innovation. Now, this one can get overlooked by academics sometimes, who toil away in labs trying to make cool new technologies, but may not take enough time to appreciate how important a go-to-market strategy is, or a new way of raising capital, or a new way of accessing your customers. We're going to talk about how business model innovation has been used already to finance a range of clean energy projects. And we're also going to talk about how we're already in a position, by using business model innovation, to deploy existing technology to meet needs that have never been met before. Electrifying rural villages in Africa, for example. But what if we can't get there with just the technology and the business model? What if innovation in both of those two sectors is not sufficient? Well, in that case, we're going to need public policy. We're going to spend 4 weeks on public policy, starting first with why it's important to balance innovation into new technologies with deployment of existing technologies. The latter can reduce our emissions today, but the former, innovation and new technologies, are necessary to drive deeper emission cuts tomorrow. We're also going to talk in week 12 about how we fund all of this. Where does the money come from? Some of the money can come from the private sector, but which entities are going to provide it? Is it venture capitalists, as has been the case for other sectors? Or are we going to need new kinds of financing? And how can public capital provide leverage for the private sector? Weeks 13 and 14 are going to be the core of the public policy unit, where we talk about recommendations here in the United States to create an innovation ecosystem. And finally, week 15, we'll talk about how the United States, which is the largest funder of clean energy research and development and kind of the center of innovation activity, can benefit by cooperating, collaborating with international partners, and the world can benefit as well. And we're going to explore many models for how international collaboration and cooperation can ensue. What are we hoping to get out of this course? Well, the first objective is for students to achieve technical fluency. Now, technical fluency does not mean that you will graduate with a degree in material science. And now that's important. We need more material science majors, but it's not important for every single person in this field to have a material science major. What is, in fact, important is that everybody can kind of speak the same language. That if I talk to you about kilowatt hours, or I ask you what the components of a wind turbine are, that you'll be able to answer with at least a basic technical understanding. And moreover, you're going to appreciate what the real research frontiers are. You'll be able to pick up a technical paper and say, this technical paper is about increasing the energy density of a battery. And that's important because the more energy dense your battery is, the lighter it can be and the farther your car, your electric vehicle, can go on a single charge. So that's the sort of technical fluency we're going to endeavor to achieve. The second bucket of learning goals is to grasp the economic fundamentals. Economists have made a lot of progress in understanding what it's going to take to enable a clean energy future. And that's everything from understanding how carbon dioxide and greenhouse gas emissions create externalities that our economic system, our market system may not internalize. But it also involves the economic theory behind innovation and what it's going to take, what kinds of incentives it'll take for companies and entrepreneurs to get their technologies funded and deployed at scale. Finally, it's important to assess different policy options. The first thing that I would urge policymakers to do, and some of you may be aspiring policymakers, is to do no harm. That's what a freshly minted doctor pledges to do. I think that public policy, even well-intentioned public policy, can too often stray into policies that are harmful to innovation rather than helpful. And once we figured out how to do no harm, let's then figure out how to build a constructive innovation environment. We're going to assess the various policy options to do so. So that's the course in a nutshell. If you're still with me, I tell you what, let's go through an example of a recent set of arguments that make the case for why clean energy innovation is so important and why I think you should be taking this class. Bill Gates called this article in Foreign Affairs that my colleague Teryn Norris and I wrote the best arguments he's read for why the United States should invest in an energy revolution. And when he says an energy revolution, he really means an energy revolution centered on and anchored by innovation, which is why the subtitle to this article is Fighting Climate Change with Innovation. Let's walk through some of the premises and conclusions of this article. The imperative is where it all starts. Climate change today undeniably is a problem, and at the Paris Climate Change Conference in 2015, we finally saw some serious progress. 195 countries all committed for the first time to make climate action plans, to actually pledge to do something on climate. Now, many argue that Paris was not ambitious enough, and they're right. But measured against a very modest expectation, the Paris Climate Change Conference at least proved that policymakers around the world are willing to do something. That represents progress on one of two fronts. The front it represents progress on is policy. But where we don't have enough progress yet is innovation, on creating the technology options that are going to make public policies politically palatable. That's going to make India, for example, be willing to deploy clean energy at a grand scale to replace its coal infrastructure without compromising economic growth or energy access for the 400 or so million people who don't have reliable access to electricity today. So there was a lot of publicity and hype around Paris. I was there, and you see numbers thrown around, $329 billion invested in clean energy just in 2015. But the discouraging countercurrent to these encouraging investment flows is that investment in clean energy innovation has actually fallen. If you take the sum of all of the public and private spending on clean energy innovation, that's R&D, that's scaling up innovative companies, you find that it's actually fallen 15% over the last 6 years. And that is extremely alarming, because we're absolutely going to need new technologies to decarbonize the world. Our existing energy technologies can achieve some emission cuts today, but they're not going to be enough down the road in the long term to achieve a near zero carbon energy system in the future. So we're going to need new technologies, and in particular, we're going to need to decarbonize the power sector. So in order to do this, we really ought to learn from the past. We should take advantage of the lessons that we've learned, especially here in the United States. And in the United States, we've had two very instructive periods. Two periods of boom and bust cycles where clean energy investment rose and then it collapsed. The lesson to take away is not that clean energy innovation investment is a hopeless cause, but rather we've really got some lessons here to learn from. The first wave in the 1970s taught us that government support for clean energy innovation needs to be sustained and it can't be slashed rapidly. And the second wave of clean energy innovation that we saw was between 2006 and 2011, just in this past decade, and it was driven by the private sector, by investors in Silicon Valley. Unfortunately, we learned there that the Silicon Valley venture capitalists may not be the best model for funding clean energy innovation. We might need a new model. So where do we go from here? Well, we now have an opportunity moving forward, an opportunity to jumpstart clean energy innovation and learn from the past. America is going to be central to any innovation revolution. It must be. America has the most innovative economy in the world, and we spend the most on clean energy research and development. And finally, we've learned the most from our previous boom and bust cycles. And what we're going to need to do is to support the development and the deployment of clean energy technology by tying together those three strands of technology, business model, and policy innovation. And finally, America is also going to have to collaborate and cooperate with its international partners. And that's going to require something I like to call co-opetition, a healthy balance between competition and cooperation. Starting with the imperative. Why is the power sector so crucial? Well, as we alluded to earlier, the power sector can control decarbonization, or reducing greenhouse gas emissions, downstream as well as upstream where it resides. If you look at these charts from the International Energy Agency's Energy Technology Perspectives report, one of the readings on our syllabus for this term, you'll see that renewable energy is the single largest contributor to achieving what the IEA and others have called for, a 2 degrees limit in the rise of global warming. Now, many dispute whether 2 degrees really is a good target to be shooting for. It may actually be unrealistic moving forward. But the point here is that for any significant, substantial reduction in greenhouse gas emissions, we're going to need to have a considerable amount of renewable and clean energy upstream in the power sector. So that's where we're starting. And that's where we're going to focus this course on. Unfortunately, as we alluded to, despite all of the progress in deploying existing technology, and I'm talking about solar panels and wind turbines, it's unfortunately the case that we've done a disservice to emerging and advanced technologies. And in fact, the existing technologies could lock out the advanced ones. This is a phenomenon known as technology lock-in. It's well known in the economic literature, and it happens when an existing technology occupies such a dominant position in the market, and there are incumbents and market structures that prevent innovation and the emergence of a new set of technologies, even if those new technologies would be superior. We're going to study this in depth later on in the course, but I wanted to give you a teaser as to what lock-in is and why we should be worried and not just elated that there has been an increase in the deployment of existing solar, wind, and other clean energy technologies. Let's look at that graph in the top right-hand corner. There you see two curves, a brown curve and a blue curve. Now the brown curve is telling you how over time the cost of a first-generation technology, could be a solar panel, declines as you produce more of it. So over time, that cost is going to come down because factories, for example, are going to get more efficient at producing the same product. Then you've got the blue curve. The blue curve tells you how cheap a challenger or a second-generation technology could become if it were to enter the market and achieve some scale of production. Now you can see initially it's very expensive because no one knows how to make it. But over time, as it enjoys the same sorts of scale gains as factories figure out how to produce that new technology as they did for the first-generation technology, its cost declines as well. And its cost declines below the cost of the first-generation technology. The problem is we may never get there because there's that barrier right at the beginning where investors say, hey, it's way too expensive to produce the first few units of this new product. Let's stay away from funding it. That barrier to entry for a new technology is what contributes to technology lock-in. And that's bad because existing technologies may not be sufficient to get us where we need to go. So continuing with the solar power example, the Massachusetts Institute of Technology released a report in 2015 arguing that even though solar power looks competitive today, it's not going to be competitive down the road by 2030 or 2050 if we need a whole lot more of it. Because the more solar power that you have on a system, the more unpredictable energy you have, and the less valuable that energy becomes, simply because it's intermittent. As a result, solar power needs to fall by a factor of about 5 in cost from today's levels through 2030, 2040, 2050, if we're really going to have solar power account for about 30% of the world's electricity. And that's a benchmark figure that most folks think will indeed get us to the emission reductions we need to avert catastrophic climate change, or at least give ourselves the best chance of doing so. By the way, my favorite quote from that previous slide was Nate Lewis's suggestion to think potato chip, not silicon chip. And solar power is not the only example of a clean energy technology platform that has experienced this technology lock-in. In fact, there have been examples in the past, like nuclear power, that are very clear examples of lock-in. And in nuclear's case, it's not just the economic advantage of the first generation technology, the light water reactor, or LWR. But in addition, public policy really helped to entrench this one particular technology. Thanks to Admiral Hyman Rickover in the US Navy, every single submarine, aircraft carrier, and then civilian nuclear reactor in the United States, and then abroad, was an LWR. Hence, we've become locked in to that one design. In the future, batteries may be the next technology platform where lock-in takes root. We're already starting to see in batteries, lithium-ion batteries to be precise, the same sort of trend that we saw with silicon solar panels, the first generation solar technology. In lithium-ion batteries, car makers like Tesla or China's BYD are starting to mass produce lithium-ion batteries. And as they do so, the cost of producing those batteries will fall. But lithium-ion batteries may not be right for electric vehicles or for powering the or for storing energy on the electricity grid. And the reason for that is they may not have the energy density, the lifetime, the safety, or the cycle rate that we need out of our battery of the future. Unfortunately, if we continue on this path, we're going to lock ourselves into a lithium-ion paradigm. And that would be bad, just as a silicon solar paradigm would be bad, just as a nuclear light water reactor paradigm would be bad. I finally want to end this introductory section with an illustration of how large the investment flows are for deployment of existing technologies compared with innovation into new technologies. As you look at these bars from Bloomberg New Energy Finance's 2015 Clean Energy Outlook, $329 billion was spent overall on clean energy, of which only $4 billion went to venture capital into new technologies and companies, $15 billion went into corporate R&D, research and development, and $13 billion went into government research and development. Another paltry $2 billion went into private equity support of clean energy technology innovation. The point here is to stress that balance is needed, not to say that deployment isn't important. Deployment, as we will study later on in this course, is a crucial step toward decarbonizing the world's energy systems. But we need to make sure that deployment and innovation are in balance, that we're prioritizing both, that they're sharing the stage. Otherwise, as we learned, deployment threatens to lock out innovation. So let's move to learning from the past. How can the United States learn from its previous boom and bust cycles to encourage clean energy innovation effectively in the future? Well, let's start by talking about innovation. Innovation, the way it was understood early on in the 1940s through the 1980s, and how it's understood today, and how that should inform a change in policy from the first boom and bust cycle in the 1970s and 80s. In the 1940s, Vannevar Bush, who was President Franklin Delano Roosevelt's science advisor, published a seminal paper called Science, the Endless Frontier, in which he described innovation as a linear process. You see it at the top of this figure. The linear process starts with research into basic science concepts in laboratory, then development, which is a little more applied, turning those basic science discoveries into product prototypes. Then demonstration, which is where you take a product prototype and you try and put it into the field, into a real-world condition at something resembling real-world scale. And finally, deployment, where your goal is to take this new product to as broad a market as possible. Vannevar Bush, in his report, asserted that innovation that's funded by the government should reside as far to the right as possible here in this research and a little bit of deployment area. Now today we no longer understand innovation as a linear process. We rather understand it as an iterative model, a model where all of these different stages, research, development, demonstration, deployment, are interacting with each other. That you can have a product that's being demonstrated but then causes a feedback down to the research side where scientists discover something new as a result of being tipped off by the demonstration in real-world conditions, etc. There are all kinds of feedbacks and loops. It's not simple, it's not linear, and it's not the case that if the government only supports early innovation, by which I mean early research and a little bit of development, that the private sector will be emboldened to carry on the rest of these steps. In fact, quite the opposite happened in the first boom and bust cycle. In the 1970s, we saw clean energy innovation investment skyrocket. And the reason for that was the dual oil crises of the 1970s. First, the Arab oil embargo in 1973, and then the Iranian Revolution in 1979, both of which sent oil prices sky high and created lines around the block for gas stations in the United States. As a result, you see these green bars right around in the middle to late 1970s, the green bars representing energy investment increase. There was a lot of research and development into clean energy. However, as soon as the 1980s hit, President Reagan comes to office and oil prices collapse, there's no longer as much of an incentive to invest in clean energy. Fossil fuels are providing us all the energy we need at the price we need. And in addition, President Reagan's ideology is very much in lockstep with Vannevar Bush's idea, which was, let's keep government innovation expenditure on the basic research side, and let's let private sector innovation take over afterwards. Unfortunately, what we saw was concomitant with the fall in government research and development funding was a fall in private sector investment in clean energy innovation. The private sector was not willing to take risks on projects where the government was not a co-investor. The government wasn't going to de-risk that investment. If the government wasn't going to help demonstrate the first-of-a-kind technology, the private sector was not going to take a chance. Too risky. And as a result, we saw a lot of projects that were started in the 1970s, whether they were in solar technology or energy efficiency or wind, we saw them collapse and get stranded in the 1980s. That led to a lull in clean energy innovation investment all the way for another 2 decades through the mid-2000s. There's one other thing I want to point out in this figure before we move on, which is to say that the magnitude of these bars is startling. When we think about how important a priority climate change is, it's clearly not being commensurately weighed based on energy R&D funding in comparison with other priorities like space funding, health funding, and bars that wouldn't even fit on this chart, defense funding. Now that's not to say that any of those are unworthy recipients of federal research and development funding. They absolutely are. But we simply are not doing our fair share on energy. So the second boom and bust cycle happened when the 1970s and 80s were a distant memory. Between 2006 and 2011, Silicon Valley rediscovered clean energy innovation. And over the course of those 5 years, Silicon Valley VCs invested over $25 billion in over 150 clean tech and renewable energy startup companies. Unfortunately, as you can see from this graph, from that green line, the total amount of financing started to fall sharply after 2011. And the total amount of financing in new deals, not in follow-on investments in existing companies, but in new deals or A rounds, that fell sharply after 2008. And we've never come back to the levels that we saw right in the middle of this clean tech boom and bust window. Today, in 2016, we remain at very low levels of VC investment. Many VCs have simply exited the clean tech sector. What happened? Well, if you compare the investment profiles of venture capitalists across sectors, you quickly find out what went wrong. Because the venture capital model, which, to set the context, is used to give early stage capital or financing to a company that's making a technology bet, a very risky bet, and can pay off in spades later on down the road, but is expected to fail, well, that model works great when you were talking about the software industry, when we're talking about the medical industry, but not about the clean tech industry. See, in both of those other two industries, it is okay for you to have a failure rate of up to 80 or 90% of your companies. And the reason for that is because on the right-hand side of this slide, you can see that the success of those 1 or 2 in 10 companies is so enormous that it's enough to make up for all of the failures before. Unfortunately, the clean tech companies that succeeded did not succeed with very high returns. Instead, the overall returns from clean tech companies were significantly negative. And that's why the high-risk, high-reward model simply didn't work for clean tech and venture capital. There certainly was high risk, even higher than the other two sectors, but there were much lower rewards. So where do we go from here? That's what I want to talk about for the rest of this term and this class. I want to talk about the great opportunity that lies ahead. I want to say that the lesson that I take from these boom and bust cycles is we fell on our face, time to dust off and get back up. How are we going to accelerate innovation? Here's where public policy can step in. The first thing that we can do, and we learned this from the first boom and bust cycle, is to increase research and development funding. Now, President Obama has already committed to doubling United States research and development funding, which accounts for about half of the world's funding. And on top of that, the United States led a coalition of 20 countries that announced at the Paris Climate Change Conference that they were all going to increase their research and development funding by doubling it in line with the United States goal by 2021. If all 20 of these countries, which collectively account for over 80% of all of the world's clean energy research and development funding, if all of these countries follow through, then we could end up with about $30 billion in clean energy research and development annually by 2021. That's a crucial first step. And we need that to be a sustained amount because as we saw in the 1970s and 80s, a boom and bust in government support leads to a boom and bust in private support, leads to a bunch of stranded projects and no sustained technology improvements. The second pillar of public policy has to be to support demonstration of projects that get investors excited to invest even more. We need to bring the private sector along on this ride because public sector research and development funding just isn't enough, in contrast to what the United States' old antiquated model of linear innovation used to be. There have been many proposals to fund projects that are called demonstration projects. The first major solar panel installation, or the first nuclear reactor that's a small modular reactor, or a reactor that's sized small enough to power just a city or town's energy needs. One of the more popular proposals came from Bill Gates. He and a series of other American business leaders called the American Energy Innovation Council have argued for a politically independent, federally chartered corporation that would make investments in demonstration projects. It's important to keep these things politically independent because we've seen United States federal support for demonstration fall victim to political caprice. The United States Department of Energy's loan program offered a $500 million loan to a solar company called Solyndra. And when Solyndra went bankrupt in 2012, that grabbed headlines during the 2012 presidential campaign between President Obama and Mitt Romney. So in order to get away from what's become a very politicized process, today that loan guarantee program can't make bold investments anymore simply because of the scrutiny it went under. We're going to need a politically independent means to do this. In addition, the United States federal government can help private corporations invest in research and development by helping fund corporate consortia or partnerships where corporations say, we may not have the resources to do a full R&D program ourselves, but we would be willing to pool our resources and do an industry-wide program. That's something where we can all recognize the benefits and then compete on who's got the best product. but the basic research and development ought to be funded not only by the federal government, but also by corporations. This also could make corporations more likely to acquire innovative startup companies in the clean energy innovation space. And that's one of the ways that you could increase the return profile, the attractiveness of the investment in clean energy innovation companies. Finally, we need to balance deployment and innovation. And so the third public policy pillar is to make sure that deployment policies are not creating a non-level playing field, an uneven playing field between existing clean energy technologies and advanced innovative ones. For example, today we have a set of policies like tax credits for solar panels and wind turbines that really supports existing mature technologies where companies already know how to make those products, silicon solar panels, conventional wind turbines, and are able to take advantage of these tax credits. Unfortunately, innovative new companies that, for example, make solar panels out of brand new materials, they don't have the scale necessary to take advantage of these tax credits in a competitive market where the silicon solar panel will win any competition or competitive bid. And so we need to level the playing field. That means explicitly offering carve-outs for emerging technologies. There's this myth that if you have a technology-neutral policy, a policy that doesn't say anything about which sorts of solar panels are going to get the benefits, then you've made a fair policy. Unfortunately, a technology-neutral policy is implicitly a biased policy toward existing technologies. The second thing that's important to level the playing field between existing and emerging technologies is to offer emerging technologies what are called stepping stone or niche markets. These are initial markets that these technologies can access without fear of being competitive with incumbent technologies or existing technologies, and where innovative emerging technologies can achieve some scale so that they come down the initial part of that cost curve and then can appeal to a wider market. So for example, light-emitting diodes. These are highly efficient lights that you can now buy at Home Depot for less than $5. Light-emitting diodes got their start not in the home lighting space, but rather in a series of niche and stepping stone markets that included electronic displays, for example. Now, if we're going to follow the example of LEDs, which are a very successful example of technology succession, of a highly efficient technology taking over from a less efficient one, we ought to use government policy to try and create these stepping stone markets. And so that's one of the themes that we're going to explore in week 13 and 14, where we try and create policies for a national innovation ecosystem. I want to leave you with two sets of images. On the top row here, you see 5 wealthy billionaires. Many of them should be familiar. And they're 5 of the 28 wealthy billionaires who have committed under the moniker Breakthrough Energy Coalition. They've committed to fund clean energy innovation, early stage technology projects, companies, and research in a way that is going to solve the problems we had in the earlier boom and bust, that learns from the lessons. These investors have promised to provide patient capital, by which I mean capital or financing that they don't expect a return on within just 5 years, which is what venture capitalists expect. And it's going to be enough capital to allow these companies to really achieve a level of scale that's more than what they would have achieved just using private venture capital money. And in addition to these private investors, you've got public governments. This is a picture of the 20 governments in mission innovation at the announcement at the Paris Climate Change Conference, pledging to increase research and development funding and doubling it by 2021. Together, these two efforts should inspire us to say that now really is the time to seize this opportunity for clean energy innovation. For me personally, this picture sums up why I'm so excited. This is a picture of 6 different coatings of a perovskite solar cell. By the end of this course, you're going to have to say perovskite 10 times fast. And a perovskite solar cell, as we'll explore in the solar unit, is a brand new revolutionary way of making solar energy that can make a coating rather than a panel flexible, cheap, lightweight, and highly efficient. we can basically do anything we want with these perovskite solar cells and coatings so long as we invest in the research, the development, the demonstration, and ultimately the deployment of that technology. That's why I'm excited, and I can't wait to walk you through the 15 weeks of this course where we'll see all the ways that scientists, entrepreneurs, firms, and policymakers together can make a more innovative and clean future.